So welcome everyone to this week's Origins Colloquium. It's a pleasure to welcome Antranik Sefilian, to present the talk this week. So Antranik received his PhD from University of Cambridge, working with, advised by Roman Rafikov on the self-gravitating debris disks. And we will, I think, maybe hear about some of that today as well in the presentation. He was an Alexander von Humboldt postdoctoral fellow at Jena University before becoming a 51 Pegasi fellow now at the University of Arizona. And yes, Antranik, welcome to the Origins Colloquium, and we look forward to your talk.
Great. Good morning, good afternoon to everyone, and thanks for having me here and for the introduction, Jonathan. So yeah, today I'll be talking about what I've been doing over the last couple of years, I guess now, on planet debris disk interactions and the role of disk gravity in that. So to begin with, well, before I begin, actually, I asked Jonathan if it would be possible to be interrupted during the talk, just because, it's a virtual talk and sometimes it can be a monologue. So I guess, you're free to interrupt me whenever, and we can see if we can, answer questions right away or keep it for the discussion. Sure. Okay. So to begin with, I guess I have to first define what debris disks are, because that's the keyword in the title. And this is my brief introduction for it. Debris disks, if you want to think of debris disks, then you should think of them as the extrasolar analogs of the asteroid belt and the Kuiper belt, which exist around other stars. And if you actually look around in the solar neighborhood, you will find that they are pretty much common. They exist about 20 to 30% of the main sequence stars in the solar neighborhood. And the gallery here that I'm showing is actually not published yet. It should be soon. It comes from a large ANNA program called ARCS. And what I'm trying to show here is, if you just take a glimpse at the figure, at the plots that you see, is that there's a zoo of structures in these extrasolar Kuiper belts. So you can see that some of them are actually narrow and they could be eccentric radially, and some of them are wide radially, and they also have some substructures within them, such as gaps, warps, and spirals. And I guess what drives, so I'm a theorist, and I guess what drives theorists in this field is basically the solar system. We know in the solar system that, the asteroid belt and the Kuiper belt are sculpted and shaped by the known planets that we have, especially the giants. And so what drives theorists in the field is that if we understand theoretically how planets can sculpt debris disks in planetary systems, then we can use the observations of debris disks and invert that to figure out where a planet could be hidden in planetary systems. So that's the broad motivation for studying planet debris disk interactions in a theoretical way. And we've been doing this for a couple of decades now, maybe 2 or 3. And as the title gives it away, we think that planets, which are not yet seen in planetary systems, can actually produce most of the observed structures in debris disks. Okay, so whether that's, let's say, the location of the inner edge of a given debris disk, or gapped double belt structures like this one, or eccentric structures, warps, spirals, and so on. So we think that the answer is almost always a planet which is hidden in a debris disk hosting system which is showing such a structure. In this talk, I'm not sure if I will make it in 30 minutes, but I want to touch quickly on the yellow ones. So I want to first begin with gaps, and then move to stirring, and then to warps. We'll see how far we go in the talk. So, okay, so we do think that planets sculpt debris disks. And you can then ask, all right, if we take all of the predictions that we have based on debris disk structures that we've observed and put it in a plot, such as the one I'm showing here, what do we learn? Okay, so this plot is basically the classical album of planetary mass is a function of same major axis. The black dots that you see here are actually exoplanets that we've detected via traditional hunting methods, right? Whether that's radial velocity, transit method, direct imaging, and so on. And the color points that you see are basically predictions up to this point. They have been predicted based on structures that we've seen in debris disks. Different colors mean different things, but that's not important for this talk. But what's important to take away is that it seems that debris disks allow us to probe a region in this classical figure where we don't know much of planets, right? So the inferred planets lie from tens to hundreds of AU from their respective stars, and their masses can be anywhere from a few Earth or Neptune masses to a few Jupiter masses, okay? Which is exciting because, we don't have a way, at least, apart from perhaps JWST, to detect planets in this region of the parameter space. And that's the hope. That's the hope. JWST is now in the sky. It's been a couple of years, I guess. And the hope is that, in the near future, most or, a few of these planets which have been inferred based on the debris disk structures should be observed. And, I'm just showing here a very rough JWST limit of what it can detect. So hopefully, we will start detecting some of the predicted planets theoretically. Right. Having said that, I guess I also have to, give this disclaimer that I think, to the best of my knowledge, the only apparent success of scribing debris disk structures to planets has been the story of Beta Peak. Okay, Beta Peak, the debris disk of Beta Peak was first observed in the 80s, which is what you're seeing here on the left. And we realized that, there's a warp, there's some vertical structure in the debris disk, and theorists were excited, saying, great, this should be explained by a planet in the system, which got predicted theoretically. And then, a decade or so after the theoretical prediction, such a planet was actually directly imaged, which is what this animation is showing here. And we think that this planet is actually responsible for the warp observed back in the 80s. But again, this is, I guess, the only successful story of linking structures in debris disks to planets and actually finding them after predicting them. I guess that's my quick introduction for planet debris disk interactions, and I want to jump into where my work comes in. I think this is a critical gap in our theoretical modeling efforts of debris disks. And that has to do with the disk gravity. So coming back to the title of my talk, so just so I clarify what I mean, of course, theoretically, we invoke a planet by hand, right? So we do account for the effect of the planet on the planetesimals within the debris disk, the objects in the debris disk. But rarely we account for the back reaction of the disk, the collective disk on the planet. And almost very, very rarely we account for the self interactions between the small objects in the disk itself. Okay, which in other words, it means that we're just assuming that the debris disks are massless, and that is at odds with observations, because observationally we know that there's some dust, it has some mass, and if you account for collisional cascades and some other technical details, we know that debris disks should be anywhere from a few Earth masses to maybe hundreds of Earth masses in total, okay? And this has been ignored in the literature by and large. So in the remainder of the talk, I will try to cover 3 cases where I do account for the effect of the collective disk gravity and see how our planetary inferences are changed by doing that. I will first start with a coplanar setup. So you have to imagine, a star orbited by a planet on a coplanar orbit, and there's a initially boring, no structured disk exterior to the planet. And this will be important for gaps, as I'm showing here with the, ALMA images of 3 famous gap debris disks. Just so I clarify what I mean by a gap is basically, I guess it can be easily seen in this figure. If I just show, surface brightness is a function of radial distance, what you see is that, the disk has actually 2 belts, and the 2 belts are separated by some depletion in between. So you can think of them as the asteroid belt and the Kuiper belt, right? That's a double belted or gapped debris disk. And I guess, the quickest intuition is that, if we see double belted disks or gap disks, then we think quickly that there should be a planet, or at least one planet, orbiting within the gap itself. Again, you see this in the solar system, right? Between the asteroid belt and the Kuiper belt, there are 4 giants which have cleared their orbits, sculpting a gap in our solar system's debris disk. So that has been the, one of the most, famous explanations for gaps in debris disks. And of course, people, including myself, are searching for such planets because it would be pretty cool if we find them. But until we get the rule out the presence or absence of such planets in gaps, I was spending time trying to find alternative explanations for such structures. And this is the setup I will use. Okay, so I have star, I have a slightly eccentric planet initially orbiting the star, and there's the initially circular debris disk exterior to the planet. And what I will do is that I will account for, the collective gravity of the disk. So the disk collectively has some mass, and that mass is non-zero. I will not discuss how I do this, but if you're interested in the discussion, we can of course discuss all the technical details. But it's basically a semi-analytical method that I use. It's not M-body. M-body is very expensive, and I like my paper and pen, so it is not M-body. It's something that I call N-ring. Okay, so first, a quick animation from a paper I like by Mark Wyatt in 2005. So this is the same setup that I showed. But I will first show results for a massless disk, just so we have something to compare with, right? So we have a massless disk. This is the orbit of the planet, and the disk is exterior to it. And now if I launch the animation, what you will see is that the disk quickly develops a spiral arm, which begins at the inner edge of the disk. The spiral arm is a transient feature. It goes out towards the outer edge of the disk over time, and at T infinity, the spiral goes away and the disk becomes slightly lopsided and eccentric depending on the eccentricity of the planet. Okay, so that's the classical picture that we have in mind. And now I will repeat the same simulation, but we will ascribe some small non-zero disk mass and R. And in this case, you will see that we launch a spiral initially that goes out, but after some time, we start developing this gap structure without actually, imposing a planet to be existing within the gap itself, right? So the planet here is actually sculpting a gap at a distance. There are many cool features I can talk about, but I will run over time, of course. But, maybe you already noticed that the gap was initially crescent shape. It was eccentric. And then, over time, it becomes more and more circular, which I think is important because, some of the gaps that we see in the debris disks are crescent shaped and some of them are actually circular. I'm not discussing the physics here as well. If there are any dynamicists in the group, their pseudo resonances, we can discuss it later. But, it turns out that you can actually derive a nice closed analytical equation to figure out when this will happen, when this outcome will happen. And all that you require is actually that the disk mass is less massive than the planet mass. Right. So, of course, this has, many observational implications. Disk HD 107146, the common explanation is that a planet should be within the gap itself. And what I'm showing with this complicated figure on the right is that, there's an alternative, right? If the disk starts, let's say, at 30 AU, we don't need the planet to be within the gap itself further away in this plot, but rather there's a sweet spot, which is shown with this, white unshaded area, where a planet could actually lie interior to the disk. And, if the disk has enough mass, in this particular case, the enough mass is defined as 3 to 100 Earth masses, then the planet can actually sculpt the gap, both its position. We can explain both the position of the gap, the width of the gap, as well as the depth of the gap and some other technical details. And so, maybe we shouldn't, if we don't find planets within gaps, we shouldn't be, disappointed. The alternative is that the planet is actually orbiting closer to the star, totally interior to the disk, and still explain the features that we see in this system. I guess the smoking gun for this theory is this particular system called HD 206893. So we already know observationally that, this star has two, very massive, actually, brown dwarfs orbiting interior to the disk. And the disk is actually gapped. There's like 27 AU gap at 75 AU. And of course, we're still looking for planets within the gap itself. But, if I just run the numbers of the system, right, take the parameters of the brown dwarfs and run it through the theory that I showed and ask, what's the disk mass that we need to explain the position of the gap, the depth of the gap, and so on, then a number pops out. The number is 170 Earth masses for the disk, right? Which means if the disk is actually that massive, and it can be, then we don't need to have a third planet in the system, and the companions that we already know of are actually sufficient to explain the observations of this particular system. This brings me to the end of the first part of the talk. I may take questions if you want before I jump to another topic.
Well, I did have a question, if it's okay. So, is there a limit on the actual observed mass estimate of that disk and how it compares to 170 Earth masses? And perhaps you can remind us how easy it is to measure the mass. So you probably can hide a lot of mass, I guess, in big things.
Exactly. Just like a small introduction, of course, when we observe disks, we observe with telescopes, right? So we have wavelengths from micrometer to millimeter, and the observational wavelength is, equivalent to the size of the particles that we see. So, the largest particles that we see in the disks are millimeter sized, which are short-lived because the system, through radiation pressure and so on, will try to get rid of such small particles. And so we need, a collisional cascade between larger kilometer-sized planetesimals that we cannot observe to, continually replenish to observe dust. So when observers, observe a given disk, you can measure the total mass, let's say up to millimeter-sized objects, and then you have to invoke some collisional cascade models to, extrapolate that to larger objects that we cannot see. And if you do that exercise for this particular system, actually the 170 Earth masses is not too far off. I guess the collisional cascade models require 200-ish Earth masses for the system.
Great. Any other questions for? Yeah.
Yes, I also had a question. Exactly when you showed here now with the 2 planets on the inside, because previously you were talking about 1 planet on the inside. Is it actually helping or making it more difficult to create this outer gap if you have multiple planets, or if you have not just, because these planets are also with 3 AU and 11 AU already quite far out. If you add 3, 4 interior planets, does it help or does it destroy the gap again?
Right, that's a very good question, actually. So yeah, the presence of more than 1 planet makes the limits on makes the minimum disk mass required much higher. So it becomes more difficult because you have to think of them as competition. Like the disk is competing with the disk gravity is competing with the gravity of the planet. So the stronger the planets are, the stronger this gravity should be, and you cannot make this gravity as strong as you would like because you cannot exceed, let's say, 1,000 Earth masses or so for the disk. So it becomes more difficult, and that's what actually I had a master's student, Mark Freebe, who just defended a month ago or so. He he generalized my theory for 2 planets, and that's exactly what he studied in the thesis. He's preparing a paper now, so hopefully it goes out at some point this year.
How about resonances? Like if they're in a 1 to 2, 3 to 2 or something resonance, would that again
that has been studied. That has been studied in actually 2006. I guess it's a paper by Tabeshian and Wiegert. The gaps that you can sculpt with mean motion resonances, the conclusion are not observable with current technologies. So the gaps that they can sculpt is very narrow. You can sculpt, 1 to 5 something AU gap rather than 20 or 30 or 40 AU gap.
Okay. Cool. Thank you.
We should let you continue though, but so thanks, Antronik. Please go on.
All right, perfect. Okay, so I quickly gave a quick introduction on what the collisional cascade is, right? The idea that we observe dust. Dust is short-lived, and we need a mechanism to continually, replenish the dust that we see in the disks, and that's called, stirring. That's a technical term, but that's what it means: stirring of planetesimals. And so now in this, second part of the talk, I want to still focus on the coplanar setup. But rather than having disks which are less massive than the planet, we'll have the opposite. Now the disk is allowed to be more massive than the perturbing planet in the system, and we'll see what happens in that scenario. So yeah, I guess these are not useful now. The idea is that planets easily stir disks, especially if they are massless, as we will see. The idea here, the assumption here is that, planetesimals in the debris disk phase are born on cold orbits. So circular, coplanar, they collide non-destructively. Whether that's, like a good approximation or not is a separate topic, but that's what the common assumption is in the field. And so because that's the situation, planetesimals won't be colliding, won't be producing dust. And so, of course, if you invoke a planet by hand on an eccentric orbit, it will make the orbits of the planetesimals eccentric, increasing collisional velocities and making their collisions destructive. And that's the classical picture of how we can, stir debris disks and produce dust. Planets can do this easily. Why? Because in technical terms, it's exactly what I just said. If you put a planet somewhere interior to the disk, then, if you follow their eccentricities, which is a proxy to the collisional velocities, then you will see that, you can have high enough collisional velocities within the disk so that your collisions are destructive throughout the entire disk and you produce dust. Of course, like how do you define what's enough depends on microphysics, like the sizes of the planetesimals, what are they made of, and so on and so on. Here I'm showing, the limit beyond which these collisions become destructive based on, whatever is common in the field, assuming basalt objects and so on. And you can see that, the eccentricity imposed by the planet is higher than this almost everywhere within the disk. Now, this is for a massless disk, right? The planetesimals are all individually massless. They have no collective gravity. They are just subjected to the perturbing potential of the planet that you invoked. So you can then ask, okay, how does this picture change if I now allow for the disk to have some non-zero mass? And that's what I will show in the next slide. Different colors are for different values of the disk mass. We're going from, low disk masses here to high disk masses here. And, I guess, again, there are many cool features as well that I can talk about. But the main takeaway is that you see that now the collisional velocities or the eccentricities of the planetesimals are actually much, much smaller than what you would have anticipated if the disk were treated to be massless, okay? Which means the collective gravity of the disk, the stronger you make it, it will hinder the planet-induced stirring in a stronger fashion as well. And for very large disk masses compared to the planet mass, you can actually just, shut off the entire stirring and the entire curve will be below what you need for destructive collisions. And again, in this case, you can, derive an analytical condition for this, which I've done here. And it turns out that for this, to hinder the planet-induced secular stirring, all that you need is the disk is more massive than the planet itself. The physics here, I won't be discussing it through the main slides, but the physics here is that if you envision now that the disk is very massive, right, you can perhaps see that the disk will cause the planet's orbit to precess over time. And, if you take a, eccentric orbit and make it precess at a very fast rate, then, as far as the disk is concerned, it will just see a circular-ish planet, right? So you shut off the non-axis symmetric perturbations due to the planet. And so the disk kind of remains circular. Planetesimals throughout the disks remain circular over time. What does this mean? Well, first I have to highlight, if we go back to this plot that I showed earlier, that we have, of course, many predictions. I didn't say that most of the predictions actually come from stirring arguments. And with this finding that disks, if they are massive enough, they can actually hinder the stirring mechanism by a planet, then what that means is that, if we allow disks to have some non-zero mass, then the planets that we think should exist should actually be much more massive to counteract the effect of the, the effects of the disk gravity. And that's what this plot here is showing. This is the inferred planetary masses for 6 systems that I chose, from this plot, from the, systems for which we had predictions before. The blue dots or the blue diamonds are predictions of planetary masses if the disk is massless. And the red ones correspond to, massive disks of 100 Earth masses, just for an example. And you can already see that, all of the inferred planetary masses should go up maybe by a factor of 3 to 10 or maybe 15 which I think is, good news for planet hunters using JWST specifically, because, planets should be more massive than what we currently think. And perhaps there are more systems in which we should be finding planets than what we would have thought if we use massless disk models. And that brings me to the end of the second part. So maybe we can do another round of questions.
Let me see if I can make sure I get this right. So you need more massive planets, and you're saying that the current limits, everything at the moment is just an upper limit, is it, from James Webb? There's no, you mentioned beta pic, nothing is really detected yet that should have been. Are there some clear cases where people are very puzzled by JWST non-detection?
I guess it has been I don't know, at least personally, it has been, not so motivating that we didn't already find some planets. I mean, there was a recent paper by a group in France where they claim, the potential detection of a planet within actually a gap debris disk. So that was cool to read, but it wasn't actually like a 5 sigma detection, I guess.
But sorry, this effect you're talking about would make the planet have to be even more massive, so that it makes these upper limits more constraining.
Yeah. So I mean, you can rephrase it, right? It could be that debris disks are stirred in a completely different way. Maybe they are born on stirred orbits already, and but if you go with the narrative that you need a planet to stir the debris disks, then if you account for the collective gravity of the disk, the planet should be much more massive than you previously thought. That's the message here. But whether, the debris disks are actually stirred by planets, I don't know. Like, you can envision other scenarios, right? Like stellar flybys or, distant companions and so on and so on.
Leon has a question.
So I guess on the plot that you showed on the last slide, where it had both the upper and lower kind of asymptotes for the so the upper limit, it looks like there are a couple ratios that are exceeding it in certain regimes. I guess why is that the case?
Do you mean, let's say, the orange and the green curves?
Yeah, the orange and the green and the red seem all above this asymptote.
Yeah. Actually, so the orange and the green curves, so here they are diverging, right? So the eccentricities at specific locations are diverging to a value of unity. And this happens because of a secular upsidal resonance. And what I didn't tell is that these are the locations where, you can actually sculpt gaps that I showed in the previous part of the talk. The position of the secular resonance can be controlled depending on the planetary same-major axis and the disk mass. And, if the resonance occurs, somewhere in the middle parts of the disk, that's where you actually sculpt the gaps that we saw earlier. And this happens, for disks masses which are, less massive than the planet, as you see here. The green is a, value of 0.5 for MD over MP. But then as you increase it, this resonance, goes away because it actually moves towards the inner edge of the disk. And then what you get is this, very sharp slope in eccentricity throughout the disk.
I have more questions on the general, expectation of masses in these disks, but we should save them for the end of things. So why don't we go on to the final part of your talk?
Sure. Yeah. Okay. Yeah. So all that we discussed so far was in coplanar setups, right? The planets and the disk were in a coplanar configuration, and I recently did some, work on misaligned setups. So we still have the same general configuration of the system, but now the planet is initially tilted away from the disk's midplane with some small inclination. And I didn't actually account for the disk self-gravity here. I only accounted for the back reaction of the disk. Okay, so the planet perturbs the disk and the disk perturbs the planet, but the disk doesn't perturb itself. I did this just because, it turns out that in this case, I can do a lot of analytical progress. And to show some important modifications even at this level of approximation. So I wanted to quickly share what I found in this study. But of course, to begin with, I guess I have to say what we expect to happen when the disk is massless, okay? Time goes down, so this is an earlier snapshot, this is a later snapshot. And what you see here is basically the classical expectation. If the disk is massless, then an inclined planet will launch a warp within the disk. And this warp over time will, go to the outer parts of the disk, and ultimately the disk will settle into this symmetrical boxy shape, which is, symmetrically located around the planetary orbit, and it will have some, thickness vertically, some aspect ratio, which is, just the initial, which is equal to just the planetary misalignment initially. Okay, so it becomes a box ultimately. Now, if we repeat the same simulation but allow the disk to be less massive than the planet, so there's some non-zero mass, then still at early stages we see that the planet launches a warp within the disk. The warp propagates outward within the disk, but at some point there's a wall, and the warp doesn't go further than that, and it develops this long-lived warp-like feature, which is actually characterized with this X-shaped pattern that you hopefully can see here, which of course is totally different than the outcome when the disk was purely massless, right? And if we now allow the disk to be more massive than the planet, then something happens at early phases. There's like some thickening in the inner parts of the disk. But if we then wait for very long times, then what we get is this picture here, where you see that apart from some excitation here, which is a technical thing I can explain later, the disk actually remains rigid to the perturbations from the planet and prefers to stay almost razor thin, with some aspect ratio, which now becomes a function of radius rather than just a constant as it was in the massless disk situation. So the disk remains razor thin-ish and rigid to perturbations from the planet. This, of course, has so many implications on how we explain warps and how we explain measured aspect ratios from observations and so on. I just wanted to share this plot quickly. It is a complicated plot, but the point is this. So we, let's say, observe the system HD 110058. We know observationally that the disk is actually warped, which is similar to the warp in beta peak. And what this plot is showing here, everything colored is ruled out based on different dynamical and observational considerations. If the disk is massless, then the classical theories would expect there to be a planet lying along this blue line, which can explain the observed warp. Okay. If we now repeat the calculation with a non-zero mass disk, then the possible solutions for the planetary mass as a function of same major axis actually broadens and encapsulates this white area. Okay, so planets no longer need to be exactly on this line, but they can actually be anywhere within this white region. And the takeaway is, if you don't want to do any complicated calculations like I've done in this plot, is that whatever you predict based on massless disk models is actually an underestimate of the planetary mass for a given same major axis, right? So for a given same major axis, the planet can be equal to or much more massive than what you would expect based on massless disk models. And there are some cool mathematical features as well. Like you can see that the solutions in this gray line, right, for different disk masses, which are shown in Earth masses unit, they all actually asymptote to this blue line at small separations from star, right? Which means if you actually predict, let's say, a planet based on massless disk models and get this blue line, and then let's say search for a planet, find a planet somewhere here, it doesn't mean that the disk is massless, right? It just means that you found a planet by luck in a region of parameter space where the solutions for massive disks actually asymptote to. And when I saw this, I then questioned, what's the situation in beta peak, right? Because in beta peak we observed the warp, we predicted the planet, we found the planet which is consistent with the massless disk calculations, and so I investigated that. in this plot, which is showing the warp production time by the known, beta peak B as a function of disk mass, okay? And what you can see if you look at this blue curve is for the given parameters of beta peak B, if I pump the value of disk mass from whatever, 0 to a few hundred-ish Earth masses, then the work production time doesn't actually change compared to the massless disk calculation, okay? Which means, the beta peak B that we detected actually lies in that, weird parameter space region where the effect of the disk mass won't be much important. So I guess we were lucky enough to use massless disk models to predict something and actually find that, seem to be consistent with our predictions. Yeah, there are other features as well. Like you can see that, to stay consistent with the age of the system, actually the theory allows the disk mass to be, up to 1,000-ish Earth masses. And so, this is another way of putting like upper dynamical limits on disk mass in a given system. So with that, I arrive at my summary slide, which, yeah. So hopefully I, convinced you that, disk gravity plays an important dynamical role, even if the disk mass is, less massive, even if the disk is less massive than the planet. And this has implications both in coplanar setups and misaligned setups. In coplanar setups, we can explain gaps without having planets embedded within the gap itself. Or if the disk is, much more massive than the planet, then we can hinder the stirring that we expect. And so the conclusion is that we would need much more massive planets than previously thought. And in misaligned setups, we can actually sculpt warps which are not transient if the disk is less massive than the planet. And in the opposite case, the disk actually can stay rigid and razor thin with suppressed inclinations and thicknesses. And of course, this all has, implications for planetary inferences and, what even perhaps motivates planet hunters to look for in debris disk hosting systems. So yeah, thanks for your attention and happy to take further questions.
Great, thank you very much. And so if you're, well, maybe people in Virginia can help. If your questions, just unmute and let us know, shout out, and I'll try moderate here. And if people who are joining online, just raise your hands in the Zoom. So are there any immediate burning questions? I have lots, but we'll start with Oliver.
Yeah, Oliver again. I had a question about your plot about the inferred masses of your planets and their orbital radii.
This one? Or
no, the one that you started from early on and have been basically quite pessimistic. Yeah, the one that came up every now and then, this one, exactly. If I see it correctly, this is like the inferred planetary masses if you don't account for any of the things that you've been looking at. And this, I think, second part of your presentation kind of raises some of these points a bit higher to higher masses. And if one then combines it with the first part,
well, the first part just gets rid of them.
First part doesn't get rid of them, but moves them significantly inwards.
Right? That's correct.
Yeah. So moving them or by an order of magnitude or even more, 2 or so inwards, isn't that even better for observations?
I hope so. Yeah, I hope so. My take on that is more from a theoretical perspective that, the gaps that we see are centered at 70 or 80 AU. And, planet formation becomes, I guess, more difficult even at such large distances. So for me, from a theoretical perspective, it feels more natural to have planets interior to the disk. So yeah, as you say, somewhere here, 10 to 30 or 40 AU rather than, hundreds of AU. So yeah, hopefully that makes things easier to be detected as well.
let me ask a general question about the disk mass, because the main thing I take from this is that you're sort of saying a lot of these debris disks could have quite high masses, whereas at least my traditional view of debris disks has been, the relatively inconsequential mass compared to planet masses, and that's presumably something that evolves over time. So younger systems, you'd expect higher masses. In our solar system, just remind us that the debris, I guess that's everything that includes dwarf planets. It would be debris mass that you'd count, or where do you draw the line? And remind us what the solar system value is. It is effectively massless in the solar system, isn't it?
Yeah. So I guess, like the quick cutting definition of debris is everything which is not a planet or a star. And so, dwarf planets and, planetesimals and asteroids and comets are all debris particles as far as we're concerned. Sure, like the nowadays value for the Kuiper belt is 0.1 Earth masses. But it could have been much larger in its infancy, right? Like there are estimates based on, I don't know, Neptune's migration, dynamical stability, that the Kuiper belt could have initially encompassed, up to 20, 30, 50 Earth masses of objects.
Right. So your effects should get much stronger in young systems if they're going to be present. Is there any hint of that then in the data?
Well, yeah. So people have looked at different correlations observationally, right? But of course, the introduction sentence should be that debris disks are typically, a few tens to hundreds of millions year old. There are some debris disks which are giga-year-olds, let's say, comparable to the solar system, but they are, much less in number. Not maybe because that they don't exist, but I guess it becomes more difficult to, observe fainter and fainter structures, right? So yeah, so the current literature reports, like I don't know, an average of 100 million years for debris disks, at which point they could be hosting, significant amount of masses in solids.
And should we? I know there are planetary population synthesis models that build up systems from planetesimals. Do they make predictions of what kind of masses should be present? And should we believe those kind of predictions?
Yeah. I forgot the exact papers, but yeah, there has been some papers showing that, you can form, I don't know, tens to hundreds of Earth masses at, 100 of AU or so. So it is possible to see such numbers as well in population synthesis studies.
Well, we can come back to it, but in general, I'm trying to think of ways to independently infer this disk mass that help, because you presented a number of solutions, which it could be degenerates, but then
yes,
how did you mention if the disk is massive, then it self stirs the planetesimals, so that would
yes,
some constraint. Does it? You know that, but of course you can always stir them with planets. Yeah.
So I guess to break the degeneracy in my findings, we have to detect or rule out planets, right? Because like if I input into the equations an upper mass limit on a planet, let's say at some location, then I can convert that to an upper limit on the disk mass and so on, right? So I guess with more constraints observationally on planets or even detections, we can then break the degeneracy as far as these theories are concerned that I showed.
Well, you had a version of this plot which had a James Webb detection limit.
So that was just a cartoon thing, but yeah.
Right, but there are systems here where James Webb should have seen something. It looks like by an order of magnitude, and having some finite disk mass made it even worse. So then you're forced to say there'd be a planet's interior, which should have been seen by RV methods, I guess.
Or is it? Yeah, for the three specific gap debris disks for which I've made predictions. They are not detectable by RV. We've checked that. Whereas, coming back to the first part of your question, so people are looking for, the most promising planets in this plot based on massless disk models. I guess it was a JWST cycle 3 proposal, which maybe they don't have the observations yet, or maybe they just, have the results now. I'm not on that proposal, but I've seen it accepted. So, there should be a paper at some point, reporting values or whatever they found for the most promising ones based on the simplified models.
But already then, in your scenario, you have a prediction of the disk mass you need.
Exactly.
Which would then say there should be some amount of stirring and so on.
Exactly.
Yeah. Anyway, maybe there's some way to complete the cycle here to make another clean prediction of. Okay, Oliver, did you have another?
I have plenty of questions. If nobody else has,
okay, we can go to Oliver, but other people, please raise your hand in the Zoom or here. Okay, go ahead, Oliver.
Right. One other thing I was wondering, like when you kind of form your gap by having an interior planet, where's the material actually going? Is it like kind of shoved around? I mean, maybe it's kind of in the plots, but is it just shoved around and pushed a bit outwards and a bit inwards? Or is some actually like spiraling into the host star, getting accreted to some of the other planets? What's happening with the stuff, basically?
Yeah. That's a great question. Yeah, I mean, to rephrase the question is, why do you even see a gap, right? And the reason for that is, as I mentioned earlier, that, we have this circular resonance somewhere within the disk. This is what this plot is, this animation will show eccentricity function of the major axis. Title displays. Okay, yeah. So what happens is at the location of the circular resonance, which is the location where we sculpt a gap, you excite the eccentricities of particles to, large values. Okay. And so you can envision then, that eccentric planets will spend more time at the apocenter rather than, let's say, the pericenter. So that's how you see the depleted area. So the particles within my model are not getting kicked out of the system. It's a secular model. So they are just spending time more at the apocenter further out in the disk than at the location of the semi-major axis. So they do remain in the simulations that I show.
And remind me, you're not really doing you're not doing n body. You said you fall n ring, but you allow these rings allow it's all accounted for, of course, where things spend more time at the apocenter.
Yes. Yeah. So rather than simulating, n bodies, right? What I've done is you can envision that every body over long time scales, over secular time scales, is just tracing the elliptical orbit that it has, right? So if you do that orbital averaging over, if you do the averaging over the mean anomalies, you'll get this orbital averaging thing. And rather than thinking of particles as point particles as you would do in a body, you can now think of them as rings. Fixed, they will have fixed semi-major axis because it's a secular calculation, but they will be allowed to rotate in space or become more or less elliptical over time.
So I was going to ask about the technical details of this ring. So each particle is modeled, is it, with a ring, and how? So you're actually following a size distribution of particles, or that's assumed, and or what? So, perhaps you can say a little bit more about the method.
So it's a purely gravitational scenario. So you can model the particles as rings tracing their orbits, and now you will have n rings describing the disk, which are also coupled gravitationally with the planet that you invoke, and all the rings, including the planet and the disk rings, are allowed to interact gravitationally. So I don't account for any size distribution because it's also justified by the fact that I'm comparing with ALMA observations, right? With ALMA observations, you're tracing, millimeter particles. You're observing millimeter particles which trace the spatial distribution of the large kilometer-sized objects, which are not subject to non-gravitational forces, right? So they will be subject to, collisional activity, but I don't account for the combined effect of collisions and dynamics in my calculations, which is a difficult thing to do, like how to wed collisional and dynamical activity together.
And let's see then, and I understand there's gas sometimes present or detected. I don't know if you want to comment on do you think the gas has any dynamical importance, or is it? And
Yeah,
so,
yeah.
what would that change anything here?
Yeah, definitely. So I haven't done any, science on that aspect, but yes, gas exists in debris disks. Some of them are, labeled as poor, so they have some, low amounts of gas, and some others are actually, rich in gas. Sometimes they are rich to the extent that it might confuse, it might beg the question whether the disk should be, labeled as debris disk rather than protoplanetary disk. So there are such instances as well in the literature. So I haven't studied the effect of gas, but there's, a growing literature on that. And, there was a paper 3 years ago or so where I was a co-author on that, where we studied the effect of gas on the aspect ratio of the disk, the vertical thickness of the disk, let's say observed in micrometer wavelengths versus millimeter wavelengths and so on. And definitely gas can do stuff, right? It can damp some orbits, bring them closer to the midplane, affecting the scale height and so on and so on. So yeah, that's a promising avenue to explore, because the literature is now active in that avenue.
But where they are detecting, I guess they've detected CO, is that right? So where they are detecting CO, is the estimated mass of gas very small compared to the kind of masses you're talking about, or could it be important?
Yeah. So the masses of CO are, 10 power minus 3 to 10 power minus 4 to 10 power minus 2 Earth masses. So they are usually low compared to the total solid mass, I'm invoking in my calculations. But that doesn't say that, I mean, if the disk is actually rich in H2, right, and we're just looking at CO masses, it doesn't mean that, the gas content cannot be higher. So it could be that there are instances maybe where the solid mass is equal to or comparable to the total gas mass. And I think that would be an interesting thing to explore dynamically. Yeah, that's my broken answer for that.
Well, then maybe at some point, maybe we can discuss later. This, I think this is our chat in Arizona was about maybe how your ring code could be applied to earlier stages as well, where we do have gas, of course.
Yeah.
Any last questions then for Antranik before we close up the main session here?
I mean, I do, but I think if I understood correctly, we anyways continue some discussions.
Time for one more question if you want.
I was wondering about observabilities of kind of the different scenarios, and not just from the perspective of observing the planet directly, but let's say we have the scenarios A, B, C, whatever, and we cannot see the planet for reasons. Is there anything that we can differentiate, and why it's like the inner planet more likely, or the outer one, or a combination, or whatever? Is that possible, or is it would the disks do look exactly the same?
Oh yeah, so that's a very nice single question that will overflow to the next discussion session.
Nice.
Yeah, so there are similarities. Okay, the short answer is yes. There are
Good.
similarities and there are differences, when you compare massless and, massive disk models. So I can speak about that for like minutes, but let's say if I just touch on the inclinations case, right, the misaligned configuration, then one of the predictions is, if you look at this, left plot, is that the aspect ratios, will have some radial dependence, let's say. Okay. I mean, traditionally, observational model fits to observations assume that, the disks vertically have a constant radially independent aspect ratio, and, they fit a vertical Gaussian for the density, right? And it turns out that, you can get radially independent aspect ratios if the disk is massless. But once you account for some disk mass and go to the orange or green curves, then you start developing, radial behavior. It can be constant in some parts and then drop as, this slope of, 1 over r power 3.5. Or it can just be that slope throughout the entire disk. But the problem is we don't have, radial fits to aspect ratios in observed debris disks. So hopefully, let's say this will motivate observers to do that and, distinguish whether, it's actually constant with radius or, it has some slope with that. And, and that will already tell us something about what's happening, whether disk mass is important, and so on and so on. So there are such predictions in all of the cases I discussed, but that will, take more time. I don't know if I can continue or we should stop at this point.
No, I think you've left it at a good place, and making predictions which can be tested by future observations, of course, is what we need to do. So let's wrap up the main session and thank Antronik again for a great talk and discussion.
Thank you for having me.